a lot of the spotlight in the quantum computing world is on superconducting qubits. They're probably one of the most famous platforms pioneered by companies like IBM that were very public and were very early also in bringing this into the cloud. And then of course also companies like Google hopping into that. But there is a second technology that is probably equally promising and also based on our production technology, which is spin qubits. And in today's video, we are going to talk about Quobly, which is one of the, let's say, premier startups in this area of spin qubits based in Europe. And if you want to learn what this company is doing, and if you've never heard about spin qubits and you want to learn how these work, what are the advantages towards, for example, superconducting qubits, then stay tuned for today's video, as this might actually give you some insights into the points that I just mentioned. And with that, as always, make sure to grab yourself something to drink so you stay hydrated throughout. And let's get started with Quobly. So here we are on their website. You see the nice silicon wafer already in the background, and silicon is something that plays a highly important role in the context of SpinQ. It says silicon-based quantum computers ready for your infrastructure. Industrial, scalable, high performance and affordable quantum computers designed to be integrated into existing infrastructure. Followed by this little remark here that Quobly secures a 150 million Series A funding. So that's the Series A is already in the 115 million, a milestone toward commercial silicon quantum computers. Now, why is there such an investment? Why is this so interesting? What is the whole story about SpinQ? So, what is a spin? Let's start with this. A spin is a property of a quantum particle that relates to its magnetic momentum or to its magnetic property. So, typically when we talk about electron spins, we say a spin can point up or down. And what do we mean by that? Well, we mean that basically the magnetic pole of the electron either goes this or this way. And that actually is something that we can use to encode a quantum state. So we can use this in order to perform some kind of information processing, because we can say if the qubit is pointing down, we call that 0, and if it's pointing up, we call that 1. Now, in order to fulfill all the requirements that a quantum processor has to have, you obviously need to be able to manipulate those states and so on and so forth. I will not talk about the exact details of how that works in today's video, but what you can basically say is if you apply a magnetic field, typically your spin will want to align with the magnetic field. So if you, for example, have a magnetic field that is pointing down, it is energetically favorable for the electron point in the same direction, so down. And that means if you're flipping it up, you need to invest some energy. And how do you do this typically? Well, you actually need to change the momentum of the electron, right? The spin, and that you can do by, for example, using a photon. So the photon gets absorbed by the electron if it has exactly the right energy, and that can actually make the electron flip up. This is very similar to what you know from other qubits which we talked about, where they might where you have electrons that are sitting on different orbits, and then you are using laser light, for example, to excite them. But actually the energy limit here, or the energy transition here, can be tuned in such a way that you can do that with electrical signals and so-called microwave photons. Microwave photons, you might have some idea in which direction this goes, because you might have a microwave oven in your home, in your kitchen. So the microwave oven in your kitchen is tuned in such a way that it basically gets the water molecules to swing and generate heat. So basically the water in your food is absorbing the microwaves, and therefore it starts to heat up. And that's also why, for example, you have to rotate the food in the microwave, because you have a standing wave pattern in there. Otherwise, the food would not get evenly hot. And there are many, many other aspects. But I don't want to talk about microwaves here. Why is this whole thing interesting? Because you can generate silicon qubits, or you can generate spin qubits with standard silicon technology, so CMOS. It is a bit challenging because you have to go down to the nanometer scale, but this is something that can already be done with today's factories, with today's technology. This is something that is being used in the latest and greatest processors that you are using for smartphones, computers, and so on and so forth. This technology stack is called CMOS. CMOS relates to specific materials that can be used in order to generate those little transistors, the little switches that are inside your processors that you have in your smartphones or in the memories that are very expensive at this point, and so on and so forth. So silicon is the classic technology, and CMOS is the classic technology that is being used to build those transistors, to build those processors. So if you could use exactly that to build a quantum computer, it would be extremely amazing, because you can use today's fabrication technologies, right? You can use the production sites of TSMC, of Intel, of Samsung to actually build quantum processors at scale. So that would be great. Now, there are a couple of other interesting aspects about silicon, silicon or spin-based spin qubits based on silicon. That's what I was going to say. And you might ask yourself, why do I know something about that? That's actually because it was the first project that I really, let's say, worked intensely on during my studies. So when I was in my bachelor's, I started to work in a quantum laboratory that was actually building back then among of the first spin qubit chips. So that was very early on in the research. It was in Aachen University. Super exciting. We had back then 2 qubits that were in silicon, and I mean, a lot of things have happened since then. But there are other reasons why this silicon platform is interesting, and I will talk to you about those moving on in this video. But for now, let's quickly go back to the website of Quobly and learn a little bit more about the company as well. So major partners, you see here a couple of known labels, like for example CEA was there, you see NVIDIA, so OVH Cloud, so big and well-known enterprises. It says Alloy Quantum Computers engineered for data centers. So you see here data center ready quantum systems, rack scale quantum computers designed for deployment in existing data centers, spanning 3 product generations with modular upgrades, turning quantum access into operational value. And that also gives us, let's say, an insight into the business model of Quobly, right? So it seems like they are selling quantum computers as additional compute resources for supercomputing centers. So they are basically selling huge compute equipment, similar to how NVIDIA is selling these AI clusters for all kinds of AI applications in the millions usually. Quobly is probably selling in the millions of cost quantum computers that you can add to existing infrastructures, to existing clusters. And then you see here industrial silicon qubits, so building quantum computers on proven semiconductor infrastructure, scalable silicon qubits on 300 millimeter wafers engineered for fault tolerant systems. So 300 millimeter is an industrial size. This is not anymore, let's say, small research wafers that people are processing, but really big systems. And I'm not sure if that also means they are selling those chips, or if it's really just to talk a little bit about the technology. Then here we see the advantage. So fully integrated 1 million qubits and control electronics in coin-sized chip and 3 data center racks built on silicon's amortized capex. And that's what I talked about before, right? So the capital expenditure of the silicon industry, the big fabs that have already been built that can now just be repurposed to build quantum chips, right? Mature semiconductor processes lower cost, and then industrial scale and requirement, thousands of identical chips, millions of qubits, and high performance qubits at 1 megahertz QEC ready, quantum error correction ready. Then applications across industries. So Quobly integrated an affordable quantum computer, integrated and affordable quantum computers enable practical applications for industrial tackling their toughest challenges in domains such as chemistry, material science, optimization, and logistics. And that's, of course, important to talk about, right? So why would anybody buy such an expensive piece of compute equipment and put it in a data center? Well, there are certain problems that we think can be solved by quantum computers very efficiently. And if you are, let's say, interested in investing into, if you are thinking you own, for example, a supercomputer or a compute center, and you are thinking, does it actually make sense to add a quantum computer in here or not? Then number one, feel free to check out our Hidden Quantum Champions playlist. There's more than 120 videos on our YouTube channel where you can learn about all the companies and the ideas and business models that they have. If you don't want to go through these hours and hours of content, but you want the express version of it, then we also have something for you, because we are working right now on a course that is going to help people to get on board and make investment decisions in the world of quantum. So if you're thinking, for example, does it make sense to buy a quantum computer, then go check out the link down in the video description where you can find more information about this course. It's targeting people that are trying to make acquisitions in the space of quantum technology, that want to invest into quantum technology, or also founders that want to understand where actually the market situation is right now, which companies are out there, and where there might be gaps to start new companies in the field. Now back to the video. So Quobly builds the industrial foundation for scalable quantum computing. You see here 2.4 plus million qubits fabricated as ST Microelectronics. ST Microelectronics as one as the premier locations for semiconductor technology within Europe. 100 plus experts working there, 65 patents that have been filed, and global locations, 5 different ones over here, just to talk about the company. And this strategic collaboration, I guess, with ST Microelectronics is very important. And now these 2.4 plus million qubits, I mean, this sounds orders of magnitude above what everyone else has, but of course this is talking about fabrication, right? So we can use the scalable power of silicon to fabricate many of these qubits, but the next step is, how do we actually control them, right? And there, silicon technology also has some very interesting property, because if you can run your silicon qubit at a specific magnetic field, so if you're ramping up the magnetic field, understandably the energy separation between my lower state, spin being aligned to the external magnetic field, and my upper state, spin being, let's say, anti-parallel in the other direction of the magnetic field, that energy distance increases. Similar to when you think about magnets, if you have a magnet and they repel each other, if you take a stronger magnet, it becomes more difficult to squeeze them together, right? And the same is true here. So the energy separation is increasing. And that is interesting because your spin qubit becomes more stable as you're doing that. There's an upper limit which you can basically not cross, because then you need to use different types of manipulation methods. So at these lower magnetic fields, you can use basically standard microwave electronics. But as you're going up, at some point you're reaching the field where you need optical methods like low frequency, like infrared, low power infrared kind of technology to access your electrons. And there it becomes difficult, but there's this certain sweet spot, and actually the energy separation is much higher than, for example, for superconducting qubits. And well, much higher is of course a question of definition, but why is this important? This is because you probably have seen the cryostat setups that are required to actually run those kind of qubits, these nice golden chandeliers. The problem is they are very, very hard to scale. So it's a very difficult engineering challenge to make them scale. And there are different approaches. For example, you could make them bigger, you could have multiple of those and try to connect them with each other, and many, many other ideas. But fundamentally, it's a very hard scaling challenge that people have to figure out. And there are now systems that claim they have figured it out. But again, I think it's not super easy. And with spin qubits, there is actually a promise that they hold that could make it easier. Because of the fact that you can separate the energy levels a little bit further, you can increase the temperature of your system so that you might be able to run those qubits at the magical temperature threshold of about a Kelvin. Now, why is that interesting? What is so magic about that? Well, this is a temperature that you can reach with pure liquid helium. Now, liquid helium probably sounds like something very exotic to you, because it is. It's nothing that we have in our daily household situations, but it is actually something that is accessible at bigger scales, much bigger scales than these dilution refrigerators in scientific labs. And also can be created using these machines that are sitting inside this box here, the basically pulse tube coolers and refrigerators, cryogenic refrigerators. And that even gives you access to orders of magnitude more cooling power, which on the one side makes it easier for you to actually cool those systems. And on the other hand, and that's also very interesting, it allows you to run classical circuits again, because you can run normal electronic circuits. Well, actually not normal, but you have to do a specific version of it. But you can run, let's say, classical chips if you will fabricate them in a specific way. You can run classical chips at these temperatures, but not at the even lower temps. That becomes very difficult because you're freezing out charge carriers on, but you can potentially operate them at these 1 Kelvin temperatures as well. And now with that said, you now have a cooling stage that has much more cooling power. You can run electronics down there, so you don't need to have all of these electronic lines going down there, but you can basically put the control electronics on the same chip with the qubits, and that way you can integrate everything using the existing silicon technology. So that's a massive scaling advantage that this technology has, because the qubits are super tiny. They are in the nanometer scale. You can highly integrate the electronics using today's existing CMOS manufacturing. So by that, you can in theory create a lot of qubits on the same chip. Now, quote unquote, you just have to show that you can really run quantum operations on those, that they're stable enough, and so on and so forth. But it's a massive promise that this technology holds, and that's why it's very interesting and a lot of people are looking into. I think I've talked a lot about the technology, but let's quickly also go through here. And one thing worth noting, so before when I went through the different points, there was something about megahertz control. I'm not sure, it's not really specified on there, but if, let's say, the energy separation is in the megahertz range, that means we have very small magnetic fields, and that means likely we cannot go up to these elevated temperatures and do the integrated cryo CMOS kind of technology. But I'm not gonna go into the details because there was not much more mentioned about that. I just wanted to quickly flag this ahead. So yeah, here we see the strategic partnership or industrial partnership with STMicro as one of the premier semiconductor manufacturers, leveraging semiconductor at scale. We've talked about that, right? So wafers are where the chips are being produced on. So they are silicon 28. That has also some profound impact, that you have to purify the silicon to one specific isotope that has no net magnetic moment to it. That's why 28 is interesting. So even numbers mean that you don't have any net magnetic property of it, while odd numbers can actually expose magnetic fields that can then manipulate your qubit. And that's something that in other material systems has been observed. That is kind of limiting the coherence times or the properties that are relevant for running stable quantum algorithms. Then, okay, there's something here about the chip, right? So scaling quantum computing requires moving from the lab to fab. And I mean, we know that chips can be made very well in silicon. Then you have the 1 and 2 qubit gates. That's also interesting. So how do they actually run, right? 1 qubit gates are obtained by applying magnetic fields to an electron spin, alternating magnetic fields, and so on, right? And then 2 qubit gates are obtained by lowering the barrier between the qubits. And then packaging, okay. We've talked about that before, right? The die is packaged and connected to a PCB that is lowered to a temperature of 1 Kelvin in a cryostat. So that is the elevated temperature that I talked about before, right? And the regime where the cryo CMOS is actually working. The control electronics embedded within the chip enable regular plug-and-play updates. Then technological, strategic, and industrial edge, right? So fast, operating at 1 megahertz at the physical level, 10 kilohertz for logical qubit, reliable, so leveraging 70 years of semiconductors to ensure reliability, and a goal of 75% to 85% disponibility rate, and then scalable industrial scale from 40 billion transistors to 1 million qubits on a single chip. Here you see the scientific advisory board. I don't want to go through all of these. They are all very well known people in the field. Since I'm based here in Switzerland, I of course need to highlight Daniel Loss, who together with David DiVincenzo created this famous set of criteria that a system has to fulfill to be able to be used for a quantum computer. So you see very knowledgeable people that have been in the field for a while, also the other ones, and then a couple of other interesting highlights about the company mentioned down here, as well as the applications and the roadmap towards the 1 million qubit target that they are looking at. I don't want to go through all of these details now, but you know, because the video has already moved on quite a bit, you know that usually I also like to quickly check out the news section to see if things are up to date. So I'm recording this end of July 2026. And we see here from July this announcement, SEAL SQ and Quobly signed $5 million US dollars commercial agreement to integrate post-quantum security into next generation silicon quantum computing platform, as well as some information here about the events, upcoming events that they are participating in, and press releases and so on and forth. Now, very quickly also about the company, right? So making quantum computing industrial, transforming quantum breakthroughs into scalable real-world systems, our mission and vision, so scaling on silicon, building quantum processors on proven semiconductor infrastructure, and industrializing quantum computing, turning quantum breakthroughs into scalable real-world systems. Our ambition is to bring quantum computing into the real world, making it reliable, reproducible, and usable at scale is what we are focused on at Quobly. And then down here we see the typical, let's say, years of history. So that the foundation in 2015, or well, actually 2000 to 2015, and then all the way up here until 2026, where the execution starts, right? First cloud accessible silicon-based quantum processor, multi-generation scaling, and some photos from the team here. Quickly about the team before we wrap up, right? So leadership team, very good to see a diverse leadership team here also, and you can also see that this is moving into a real, let's say, company. This is not just 3 people working in a garage, right? So you have chief executive officer, but also chief financial officer. So all the, let's say, different roles that are covered here, chief operations officer. So many different roles covered in the board, and the same is true for the board itself, as well as for the scientific advisory board. I think we've briefly seen that before, right? So many different people that are in here, and there's also some strategic partners mentioned down here in the commercial space as well as in the academic space and industrial financial space and so on, right? And these are the investors. Again, we see the European Innovation Council being part of this one as well, as of some other companies from EMEA or from the European Union that are launching in the space of quantum technology. So with that, I want to close today's video. I hope you liked it. Thanks for joining and thanks for staying all the way to the end. In case you like this video, please make sure to subscribe to the channel to not miss out on the next one. I'm looking forward to see you there. Until then, bye bye.